Assalamu alaikum. Welcome to lecture 17 of natural language processing. So I hope all of you are doing well. Uh, so today we will be discussing sequence modeling. We will start with discussing an application of sequence modeling, which is the POS tagging problem or task, part of speech tagging task. And then we will discuss probabilistic sequence modeling or sequence classification, and then move on to discussing a popular approach for sequence tagging from the probabilistic framework, which is the HMM, Hidden Markov Model. So that is the primary agenda for today. We will have a quiz at end of class today as well, at 11:05. So that's the agenda for today. Any questions? All right, so let's then get started. So we had started discussing part of speech tagging last time. So parts of speech are word classes or linguistic classes like noun, verbs, adjectives, and so on. And the idea of part of speech tagging is to label each word in running text with the appropriate tag from the POS tags that are available. So let's start with that again. So I'm going to use this slide, and I've also posted this slide on your LMS page. So POS tagging is basically the process of assigning a tag, and the tag is basically a possible tag from the possible set of tags which describes the word in the running text. So for example, if you have a sentence like the lead paint is unsafe, let's say this is the input raw text, and after running the POS tagger, we will get the output that is shown below, which basically has the tag assigned to each word in the running text. So the is basically a determiner. Lead here is actually a noun. Paint also is noun. Is of course is a verb, and then unsafe is an adjective. So given any running text, we would like to assign each word in that text to an appropriate POS, part of speech. I think this is discussed later on as well. Let's move forward. So what are the parts of speech? So the most common parts of speech are about 5, 6. So you have noun, verb, adjective, adverbs, conjunctions, prepositions, determiners. So these are the most common parts of speech. Of course, we are talking about English. Other languages may have, of course, most languages, all languages have some common set of parts of speech. But if you go into finer granularity, then of course, each language would have its own set of tags for the parts of speech. So what exactly is a part of speech? So you can have various names for it. So it's a word class or a lexical category or morphological a group that basically describes the words in that group. And of course, linguists discuss parts of speech in quite detail. Uh, as computer scientists, we don't spend too much time on that. We just take some tags and use them for our particular application. So, of course, as I said, parts of speech can be categorized in coarse granularity or in fine granularity. So for example, nouns, of course, is a coarse granularity, but if you can go deeper, you can have common nouns and you have proper nouns, and you may have even more finer distinctions of nouns as well as for other parts of speech that linguists might have come up with. So of course, depending on your application, you will choose an appropriate tag set. But of course, the most common and the basic is, of course, the 4, 5, 6 that I mentioned up there. So here we have some examples of words from each class. So nouns, as I said, proper noun, common nouns, so on, names of people, location, organizations, name of things, for example. So those are nouns. And then, so verbs basically are action words. So debate, study, learn, run, walk, all of these are uh, verbs. And then adjectives, good, bad, purple, um, very basically adjective basically is a characteristic of a noun. And then adverb basically qualify nouns and verbs. So usually these are words that end with a ly, excessively, closely, and so on. And then prepositions are basically words that uh, convey a relationship between nouns. So under, over, so over the chair, on the house, on the bed, besides, inside, outside. So all of these are prepositions. In determiner, of course, are the, a, the common words that are used in English. Conjunctions are words that join two segments of a sentence, and, but, none, and, but, and so on. So pronoun, of course, are kind of surrogates for nouns. So I, mine, he, she, all of those are pronouns. So peer tagging, as we said before, is the process of assigning an appropriate tag to each word in running text from the set of possible tags. So peer tagging has numerous applications. It's often a basic step that is done in many tasks. And so if you talk about speech synthesis or text to speech, so you can think of the word like live, L-I-V-E. So I've mentioned this example many times. So LIV, of course, live could be live or live. And of course, as you noticed, you pronounce it differently based on the POS of this particular word in context. If it is live match, you don't call it live, you don't sound like live match, you call it live match. So of course, for text to speech, to be able to pronounce words properly, we need to know its POS so that you can pronounce properly. For example, read and read, the past tense read is also spelled the same way as the verb read. So, and there are of course many other such examples. So and of course, POS tagging is important for some basic steps as well, for information extraction, for stemming, for lemmatization. So there are some other examples for speech synthesis given here. So parsing is another application. I think I mentioned this last time as well. So basically, parsing is trying to segment or break down a sentence into constituent parts of importance. And usually, parsing is done to get a deeper understanding of uh, running text of sentences. So, so again, to do that, uh, POS tagging might be important. For example, usually we parse sentences at the verb level. So you need to know where the verb is. So you have the subject, which is usually a noun, and then you have the object, which is usually a noun, and there's a verb between it. So again, this is one very simple form of parsing for which POS tagging is used. You need to identify the verb and you parse the sentence around it. Similarly, you can think of conjunctions. You can separate the two parts of a sentence if you know the conjunctions. So information extraction is a general task which can have any kinds of extraction from text. One of the example is named entity, which we'll talk about in, I think, detail in a couple of lectures or one lecture. But of course, information extraction could be extracting anything of interest from text. It could be dates, it could be names of persons, it could be, uh, for example, organizations. So all of this would be helped by NER. Sorry, would be helped by POS tagging. So machine translation also benefits from POS tagging, and knowing the proper tag for a word would help you better translate the word. And of course, there are other applications as well. You will see some others as we move through this course. So we need to make just to understand POS tags, we distinguish between closed and open classes. So there are some POS that are closed, meaning that membership to those POS groups do not change over time, or you can say even in space. So in English, these are usually like pronouns or prepositions and determiners. So you don't have new words coming in or other words going out of these groups. So the membership is fixed. And usually it's not very large. So if you talk about, for example, prepositions, so you have a decent number of prepositions, but not massive. So in, under, over, besides, all of these are prepositions. So you will notice that in these slides, we have used some other names for categories. For auxiliaries can be used, and you notice that this is kind of similar to determiners. Okay, auxiliaries are different, but again, articles and determiners, and so you can have finer granularities of POS tagging. So if you go into finer, so you may have tons of names. So some of those names would be, you can say, overlapping, and you should be able to distinguish between them if you look at the meaning of that particular name from a linguistic perspective. So open classes are those POS whose membership can change. And in the English language, of course, we have nouns, for example, names of persons, for example. Uh, so the names of person is not fixed. You may have someone who is born today who might be given a name that was not given to a person name previously. So again, that person would then be a noun. Then, of course, you can think of things as well. For example, the word iPhone. So iPhone is an iPad. So these are nouns, but uh, they were coined in the last 10, 15 years. So we didn't have these nouns before the 21st century. Similarly, you might have new verbs coming into play. So some way of describing some action, you might have a new word for that. So the whole idea of mentioning this is that so you should know that membership can change even for so membership can change for groups, and as such, POS tagging can be ambiguous or difficult. And of course, POS tagging is ambiguous or difficult even for the case where you have a single word. It may have multiple POS tags. So for example, we gave the example of LIVE. So it can have multiple POS tags. And then of course, you can have new POS tags or new words joining a particular group. So these slides give you some examples. I'm going to not discuss this in detail. You can look at it at your own time. So again, they have kind of done finer categorization. So these are all closed POS. So membership of these POS do not change, typically do not change. So these are finer distinctions among prepositions. So English articles or determiners. So conjunctions. Okay, so now the question is, as you have seen, you can have various tag sets. Some of them could be granular, some of them could be very fine-grained. So which tag set should we or a person use for a particular application? So of course, this is application dependent. If your application requires that the tag set is fine-grained, then you should use a fine-grained tag set. So in most applications of NLP, we usually use a smaller and kind of granular number of tags, and they are usually the 6, 7 that we mentioned earlier on. So noun, verbs, adjectives, adverbs, prepositions, pronouns, determiners, and so on, conjunctions. And even actually for some application, you might not even need all these 7. So you might need just one, maybe noun, or you might need noun, verb, and adjectives, or maybe noun and adjectives only. For example, if you want to do very basic sentiment classification or sentiment analysis, you probably need just noun and adjectives. So if you know the noun and then the adjective that is associated with that noun, you can then aggregate the polarity or the opinion that people have about that particular noun. So noun may represent some product or service that is being studied, and the adjective that appears close to it, proximus to it, would describe that particular noun. So again, application dependent, you can choose an appropriate tag set. The pen tree bank, this is a popular repository of uh, textual information, especially used for parsing. So they define about 45 parts of speech. So that is quite fine-grained. And for many applications, people do use these 45 parts of speech. And if you follow the Penn Tree Bank standard, they also have a way of, they have the categorization, of course, of the POS, and also they kind of have special abbreviations for identifying each POS. So Of course, you can look it up, and if you are using the Pantry Bank. So this is the Pantry Bank POS tag set. Some examples here. I won't go over this in detail. There are some examples of also the abbreviation that they use for that particular POS tag. So here's an example where the Pantry Bank is used to tag sentences, and of course we are using the appropriate abbreviation that the Pantry Bank has proposed for these tags. So we have discussed this before as well. So words may have multiple POS, and there's one example given here regarding the word back. So it could be an adjective, it could be a noun, and so on. So the proper adjective, the proper tag of a particular word would depend on the context in which it appears in a sentence. And that's why POS tagging can be hard or challenging. So of course, because of this, POS tagging is hard and ambiguous. So now the question is, how do you solve this problem? So given running text in a particular language, we would like to assign tags from a fixed set of possible tags to that running text, meaning that to each word in that running text. Of course, traditionally, so you can have rule-based tagging. You have defined a set of rules. So for example, in English, usually if you have a verb, then after a verb, there might be a determiner, and then a determiner, you might have a noun. So, and maybe may not have a determiner, just a verb and noun. So you can define rules like that. And linguists have done that in the past. But of course, such rules are not exhaustive and they are often difficult to maintain. So, so the more common approach that is used today is, of course, based on machine learning to let computers automatically learn the rules or the behaviors of POS tagging in running text. And you can have probabilistic models for POS tagging, as well as you can have statistical methods. So statistical method, of course, nowadays are primarily neural networks, and probabilistic methods are based on Markovian assumptions and its variants. So we are going to start with the probabilistic model approach first, and then move on to neural networks later on. So in the probabilistic model, there are two common models. One is HMM, which is a generative model, and the other is conditional random field, which is also probabilistic but is discriminative. This distinction is similar to like naive Bayes was generative and logistic regression was discriminative, but both of them were probabilistic. Here now we are dealing with sequences. We have HMM and CRF. We will not discuss CRF in detail in this course. We will discuss HMM. And then, of course, we have the statistical techniques, which are primarily neural networks nowadays. So what is POS tagging? So we are given a set of words, which is, of course, not really a set, it's a sequence of words. You can call them sequence of events. Each word is an event occurring at a particular position. And the idea is that for each word, so for each word, we like to assign a proper tag to it. So at the end of the day, we also have a sequence of tags or labels or states attached to each of those events. Okay. So now let's look at this in a probabilistic sense. Uh, so the math behind the probabilistic neural network is summarized in so these slides, sequence labeling slides. I've also uploaded this slide on LMS. So these slides are mine. So and they basically discuss the notation and method for HMM. So let me start from here and then maybe use the slides. Okay. Any questions? So, okay, so our task is sequence labeling. So we will define the task precisely and then study it from a probabilistic sense and then move forward to the HMM model, which is one probabilistic approach for solving this problem. So what is the problem setting? Just a second. So we have a sequence of events. Uh, so these events, of course, are observed. And of course, for all of this mathematical formulation, we will focus on the POS tagging application. Of course, you can have other applications as well, for example, named entity recognition, but we will take examples of POS while we are discussing this. So we have a sequence of events, in this case, sequence of words that appear in running text. We call them events, maybe in general, and of course, these are observed. And we denote this with the capital O. So O, capital O is a sequence from O1 to OT. OT, of course, T is the total length of the sequence, capital T. So what are these O's, small O's? Small O's come from, in our particular application, from the vocabulary V. So, so what is the vocabulary V? The possible words in our corpus. Okay. So what is then the sequence? So sequence is the sequence of words from the vocabulary. So O1, O2, O3, OT. So O1, for example, let's say I have the sentence, I study at LUMS. O1 would be I, O2 would be study, O3 at, and O4 LUMS, and T, of course, would be 4. And all of these O's, small O's, come from the vocabulary set V. It's a word from the vocabulary. And the size of the vocabulary, of course, as we have done previously, is the absolute or the bar of V, which can be taken as M, as we have done previously, but here we have denoted as V. So vocabulary, of course, is V1, V2, up to V total number of words in the vocabulary. So then the other thing that we have is a sequence of labels. So these labels are hidden. So whenever we have a corpus, which is running text, we just have the sequence of words. We don't have the labels associated with them. Of course, if you have a labeled data set, then usually that is labeled by some external teacher, you can say, some human being or some even algorithm sometimes, but it's not usual that you, whenever you write English, you also attach a label to it. So these are hidden. And of course, this is the capital Q sequence. So Q1, Q2, QT. up to T. So the sequence length in both of these cases is the same. Capital O and capital Q have the same length. Okay? And Q, small q, comes from the possible sets of labels that we have. So this is the tag set that we are interested in. So in this case, I've denoted with S, capital S, and S, capital S could be S1, S2, S3 to Sn. So N is the total number of tags that we have. So if we are working with just noun and adjectives, then N would be 2. Okay. And of course, we are working with a pen tree bank tag set, which would, this N would be 45. So as we will see later on, usually we will define a starting state or label as well as ending label. So this is usually S0 and SF. So the rest was S1, S2, S3 to Sn. So you also have a S0 and a SF. So starting of a sentence, for example, and ending of a sentence. So these two labels are also defined. So in this case, then the total tag set size would be N plus 2. So we have now the capital O and the capital Q. So the joint probability distribution P, probability P over O and Q. So this distribution, therefore, completely defines our sequence labeling problem, the problem setting that defined earlier, where you have a sequence of length, observed sequence of length T, and a hidden sequence of length T. The two sequences, of course, are of the same length. Okay? So if we know this distribution, then of course we can solve various things regarding this problem. So this, of course, is a generative model. So let's say you know this model, this distribution, then you can sample according to this distribution to get O and Q. So that's why this is called generative model. So you can generate the data if you know this distribution. So if this distribution is known, then of course, as I said, various problems can be solved. So let's specifically talk about 3 problems, which is of relevance to us in NLP. And these are conventionally called problem 1, problem 2, problem 3. And problem 1, of course, is also called the likelihood problem. So what is a likelihood problem? So the likelihood problem is to find the probability of O, capital O, which is what? A sequence of words, a sequence of events. So what is the probability of a sequence of words given our model? When I say our model, it means the distribution over O and Q. So if we know O, distribution over O and Q, we can find out whether a particular sequence of words, which is capital O, we can find out the probability for that. And if there are 2 or 3 such sequences, we will know that which sequence is more likely. So that's why this is called likelihood problem. So from a probabilistic sense, how would you get that? You will have to marginalize the joint distribution or sum out Q from the joint. Okay? So summing out needs to be done to find the probability of O. Okay? So for example, if I have two sentences, two capital O's, one is I study at LUMS and the other is study I at LUMS. So the likelihood problem would give us a probability for both of these sentences. And if your model is correct, which is probability of O and Q, then you'll get a higher probability for I study at LUMS because it is based on proper grammar and proper usage of POS as opposed to the other sentence. Okay, so this, of course, is the likelihood problem. So any questions so far? So the second problem, which is called problem 2 and which is also the decoding problem, this is actually the sequence labeling or sequence classification problem. In this case, given the model, which is of course the distribution over O and Q, we will like to, and also given a sentence, capital O, we would like to find the best Q for it. So sequence labeling or sequence classification problem, or as commonly known, the decoding problem. So given the distribution and some sentence, we would like to find the best sequence of labels. So in this case, of course, so you'll have to find the argmax Q for the joint distribution. So what Q gives us the highest probability for this joint distribution? And that Q would be returned as the best setup or sequence of labels for the sentence. So let's say you're given the sentence, I study at LUMS, this is cap O. We would like to find the cap Q, which is what? Determiner, sorry, I is pronoun, study is verb, and then at is preposition, and LUMS is noun. So this sequence of labels is the cap Q that we would like to find, and which is, of course, the correct answer for this problem. So this decoding problem is the sequence labeling or classification problem. And this actually is the POS tagging problem. Okay. And then we have the problem 3. This is actually the learning problem in sequence modeling. So in this case, we want to learn the model. And what was the model? Probability of O and Q. So we are now given data, and from data, we would like to learn the model. And this is, of course, learning, machine learning. And in this case, we make a further distinction of two types. We have problem 3A and problem 3B. In problem 3A, so in problem 3A, we have a labeled data set, meaning that we have O and Q given to us. Your corpus has sentences like I study at LUMS, which is O, but for each word, we also have the Q. So I would be pronoun, study would be verb, at would be preposition, and LUMS would be noun. So we have a labeled data set. And from this data set, we would like to learn the model, which is, of course, the joint over O and Q. So this is supervised learning. And problem 3B is semi-supervised learning. In this case, we only have running text, meaning that I study at LUMS and all such words written English. And we have the tag set only, not the labels, meaning that we have the possible set of tags only and just the running text, and we would like to again learn the model. So of course, as you can see, you have less information from the data regarding the problem. And this setting, of course, is the semi-supervised learning setting. So actually, more appropriately, this is unsupervised learning. Actually, it's not really even semi-supervised, uh, unsupervised learning, because you don't have any labels given to you, just this possible set of labels. So let me now move to my notes. Any questions so far? So, so probability of O and Q. So this is a joint over O, which is what? Our observed event sequence, and Q, which is hidden label. So this is our model in the probabilistic sense. And if you know this model, we can solve various problems, as we discussed: problem 1, problem 2, problem 3. Of course, in this model, we have assumed that O and Q are of the same length, and the length of sequence is T is basically the length of the sequences. Both sequences are of the same length. Of course, in general, these sequences may be of different length, and we will discuss this when we discuss neural networks. And so, for example, you might have the problem of machine translation. So in machine translation, your input sentence is, of course, a sequence, and your output in another language is also a sequence, but it might be of different length than the input. So again, as you can see, sequence modeling problem is sequence modeling in general is very powerful, and it can be it has numerous applications in NLP. Of course, here we are focusing on the POS tagging problem, in which case the sequence lengths are the same. So, and then of course, N we defined as the we defined N as the number of possible labels, and then we have V is the number of possible events, which in the case of POS tagging is the vocabulary size of your corpus, and N, of course, is the possible tag set size. So let's say, let me write this joint. So using product rule of probability, I can write this as probability of O given Q, probability of Q, right? So this is simple product rule. Of course, you can use Bayes rule as well, but Bayes rule also is developed from product rule. So if you are not able to estimate the left-hand side, which is a full joint, you can estimate the two probabilities on the right-hand side, and you will still get the full joint. So this, of course, as we said before, is the generative model. If you estimate the right-hand side, which of course has probability of O given Q. What does this mean? So given the sequence of labels, we want to find, or we want the sequence of words. And of course, this is a probability for that. Of course, given a sequence of labels, we have the distribution over all the sequences of words. And of course, if you want to select one, we will probably select that one which has the highest probability. And then, of course, the second one is probability of Q. So what is this? So this is the prior probability of sequences of labels that appear in for any given problem. Let's say for POS tagging, this is a sequence of tags that are correctly used in English. And of course, for any of these, probability of Q, this is also written as probability of Q1 to probability of QT. Okay? So it's a sequence. So this sequence is important. So let's say if you wanted to estimate this parameter, so how many probabilities would you need to estimate? So this is the full join from Q1 to QT. What is the possible number of values for any Q? Any Q can take on, as we said before, Qi is in S, right? S is possible set of labels. So in other words, you can also say Qi can be any of those S, let's say 5, small s5. So for example, again, what did I write? S5. So for example, you have, let's say Q1 could be, let's say, the tag noun. Okay. All right. So how many parameters would you need? So each value Q in the sequence can have n possible values. And you have how many? T. The length of the sequence is T. So you will need, of course, you will need to the order of basically n raised to power of T probabilities, which is going to be a huge number. So T could be quite large, N can also be large. Let's say even if it is 5, 10, T is definitely large. So you have an exponential number of parameters or probabilities that you need to estimate. So similarly, for the other probability of O given Q. So for a possible Q, you need to estimate the distribution over O. So O में क्या है? For O, of course, is capital O is basically O1 to again O capital T. Sequence length is of course same. Each of those O's, O, I, is in your vocabulary V. So for example, O2 could be, let's say, V5. Okay, so it can take any value from the vocabulary. So in this case, again, you have, so what is the possible number of probabilities that you will need? So we have V raised to power of T. So this is the possible number of O's that you have. But then, of course, this O is for one possible sequence of Q. So how many possible sequence of Q's do we have? So multiply that with the possible number of Q's, which is N as we computed before T. So this is the number of probabilities that you need to estimate for this. So again, this is a massive number. V vocabulary size can be huge in the thousands or even the hundreds of thousands. And T, of course, can also be large. N is large, T is large. So this is a huge number. So obviously, this is a very large problem, meaning that it are lots of parameters. And we would like to simplify this. Okay. So the simplification of this actually then leads to the hidden Markov model. So I mentioned probabilities. You can also think of these as parameters because you have to estimate this from data. So it's a parameter of the model. All right. So what are some of the assumptions that we make? So one of the first assumption is basically the Markovian assumption for the state transition probability. So we talked about probability of Q1 to Qt. So this was probability of capital Q. So you can always write this as probability of Qt given Qt minus 1 to Q1. And then you have the Qt minus 1 Q1 here. So this term that I've just written, you can further break it down using product rule. And as such, you can write this right-hand side as probability of Qt given, of course, Qt. Of course, I'm not being very precise with my writing of the notation, but I hope you understand. So this t minus 1 is the subscript. So Q1. And then, of course, you have probability of Qt minus 1 given Qt minus 2 to Q1 to, of course, probability of Q2 given Q1, and then, of course, probability of Q1, right? So you can write it in this way. The joint of the labels, the sequence, as in this way. And then we apply the Markovian assumption. Markovian assumption is that the current state depends only on the previous state and no other preceding states. So the current state depends only on the previous state, or the current label, I should say, to be precise, depends only on the previous label and nothing else in the prior sequence. So if you do make that assumption, then this further reduces to probability of Qt minus 1 only, and then, of course, probability of Qt minus 1, probability of t minus 2, and then, of course, probability of Q2, Q1, probability of Q1. So we have simplified our joint for capital Q into this probabilities, in which we only consider the preceding label, not all the labels before it. Okay. So in other words, the parameters that we need to estimate now are, of course, probability of Q in general, T, Qt, small t, given probability of t minus 1. So we'll need to estimate these parameters now. So how many of these would we need? So big O. So how many Qs do we have? one queue. We have n queues. And then this n queue is for a particular qt minus 1. How many qt minus 1 do we have? We again have n. So essentially, this is big O n square. So this is, of course, significantly better than the one that we computed earlier, which was what? N raised to power of t. Okay. So we have simplified our model. We have reduced the number of probabilities. We have reduced the number of parameters. Okay. So we are running out of time. So the second assumption is the assumption of conditional independence. And this is applied to simplify the first term, the term probability of O given Q. Okay? And of course, O is the sequence from O1 to OT, and Q is the sequence from Q1 to QT. So we simplify this. So each of those O1, O2, O3, OT is considered to be independent of the other given the current label. Again, there is, in this assumption, there is conditional independence as well as the Markovian assumption, the current label only. So this basically then reduces to, of course, let me first write this first. So this is O1 to OT, to Q1 to QT. Okay? So this would then reduce to the product, of course, product over all t of probability of small o ot given small q t. So instead of the joint, we now have this conditional for single observed event and single label for the same position t. So we do not look at other positions, and we also assume that the observed events are also independent of each other. So that's why they have been broken down into products. So in other words, in layman terms, we say that the current word that you see is only dependent on the current label. So QT, OT. The current event depends on the current label or state. And if you do this, of course, the big O now becomes for how many O's do we have? We have V, and then how many N do we have, which is Q? So this is reduced to this. This again is now much better than the one that we had computed where we have T in the superscript in the power. Okay. So this is the two assumptions, and when you make these two assumptions, you actually obtain the hidden Markov model, which of course is also abbreviated as HMM. So I think in the next class, we'll start from here, and then we'll discuss the solution to the likelihood and the decoding problem, and then also discuss a learning problem. So this would be done in the next lecture. So any questions? So the probabilistic approach to sequence modeling is now part of as an appendix in your textbook. It's available on the web. Before it was actually a regular chapter, but now they have moved it to the appendix. So you can read that as well. as well as I have uploaded the 2 slides on POS tagging and the sequence labeling slides. So please read that as well. In the book, previously, there was slight confusion in the notation. So that's why I prepared my own slides. So you can follow my slides for the preciseness in notation. ठीक है. Any questions? No questions?